Okay, we're going to go ahead and get started. If anybody is joining us, welcome. Thank you for attending our session today. We have a really exciting webinar on the principles of the performance-based design and integral bridges. For anybody who is new to MIDAS, we are a subsidiary company of MIDAS IT. We develop a total solution service for bridge building, geotechnical, and mechanical engineering. These are some of the software that we provide. You might be the most familiar with our MIDAS Civil. And if you join our upcoming training sessions, you'll see a glimpse of our latest software, MIDAS Civil NX. If anybody is new to this platform or hasn't joined us in a while, GoToWebinar has had an upgrade. So I did want to go ahead and provide you guys with some tools that you might need throughout the session today. If at any point you're wondering who is speaking, the presenter name will be on top. On the bottom, you will have all of the audio settings, camera settings, as well as returning or entering the chat. On top, you will be aware of any cameras that are being shared, and you can also see the session duration. On the bottom left, you can see and use the hand raise icon, not only just to raise your hand if you're having any issues or if you want to get our attention, but you can also use it to react to the presentation, give it a thumbs up or a heart. And then on the top right, you can use the question box to submit your questions throughout the session. We will take all questions at the end, but feel free to submit them at any point during the session. And if you're having any issues with your audio or your speakers or anything like that, you can edit them using the gear button on the top. And now I'm going to go ahead and present our speaker today. We have Dr. Matthias Schuler. He is a manager for structure division in Parsons. He has over 30 years of experience in the design and construction engineering of complex bridges worldwide. He is the engineer of record of I'm going to try to say this correctly, of the Cho Bridge, one of the longest cable-supported bridges in North America, and the Canal Lachain Bridge, a curved extradosed bridge. Dr. Schuler has received his PhD in cable bridges under the guidance of Professor Schleink, a structural engineer internationally recognized for his contributions in the development of strut and tie models and his design of long span bridges, roofs, and other advanced lightweight structures. Dr. Schuler has worked on a wide variety of remarkable bridges in North America, as well as Europe, Asia, and Africa, and he has been recognized for his contributions by local and international awards. His innovative design solutions have led to significant savings in construction and maintenance costs, and he is an IABSE Fellow, a former member of the TRB Committee, Construction of Bridges and Structures, an invited speaker, and has published numerous and technical papers on bridges and structural design. So I'm going to go ahead and give you the presenter settings and we can get started.
Thank you, Luciana. So let's get my presentation up here. So can you see my presentation?
Yes.
Perfect. So welcome to my presentation about principles of the performance-based design in integral bridges. This is not the typical, let's say, software presentation that you will have here in the MIDAS expert webinar. This is about the bridge design and how to create better structures right from the start when you are in the conceptual design phase. Before we get to the agenda of this presentation, I would like to define what I understand under integral bridges. Integral bridges are bridges without expansion joints and bearings. And hereby the superstructure, substructure, and the foundation need to be considered as one. Those bridges are specifically designed to reduce construction costs and maintenance efforts. They show an increased structural redundancy and resilience because they don't have the bearings and joints. And as a designer, you have a superior performance in mind when you go the extra mile to design integral bridges. And I will talk about this later more. Now, what can you expect in this presentation? I will start with an introduction. Then I want to talk about the development. I call them advanced integral bridges, not the standard integral bridges that you may know. Then I want to talk about design aspects of integral bridges, the aesthetics of integral bridges, and you can actually use those comments as well for other bridges. But I believe that integral bridges have a tremendous potential to improve aesthetics. Then I want to talk about the performance-based design and how this is relevant for integral bridges. And then I come to three examples, two of them in Germany, the Lafayette-Steg in Stuttgart-Suppenhausen, which is a pedestrian bridge, and a highway underpass near Winnenden. And then I have a Canadian example here, the Hunt Creek pedestrian bridge in Surrey, a bridge that hasn't been built yet. And before I come to the conclusion and close out this presentation, I would like to have some remarks about the future of integral bridges, because I believe we are just at the beginning. Introduction. Integral bridges have become the new standard for small bridges, and you probably know this, that integral bridges are becoming more and more common when you talk about small bridges. But I want to show those bridges need not necessarily to be small. Integral bridges allow a redistribution of forces and the activation of secondary load paths, and this is, from a safety philosophy, very, very important. Integral bridges require to consider the entire structure and soil structure interaction to optimize cross-section and structural behavior. The performance-based design approach enables designer to adjust structural behavior so the bridge responds in an advantageous way to site-specific design requirements. And I think this is something that is really, really important, and that's why I believe that performance-based design that we are very familiar with in seismic design will come as well into typical bridge design applications, because it gives you the possibility to create better structures. Properly designed integral bridges capitalize on three aspects: enhanced flexibility, globally improved structural redundancy, and amplified deformations before reaching ultimate capacity. And the last point is very important, because the last thing that you want to see as a bridge engineer is that your bridge collapse. And if your bridge is in distress, then you want that the bridge talks. And the only way that the bridge is talking to you is by showing the deformations or cracks, or that's something that is visible. Now I get to here the first chapter, the development of advanced integral bridges. And I'm starting here with a bridge that is now almost 100 years old. And you see that the idea of creating integral bridges is not new. This is Robert Maillart's Waldschild Bridge in Switzerland, has already a span of 55 meters, which you would probably today consider as an upper limit for integral bridges. And I will show you that there is no upper limit. This bridge is a deck-stiffened arch, so a very, very slender arch bridge where you have slender walls that support a superstructure. And the arch alone couldn't survive unsymmetrically distributed life loads. You need a stiffening girder, and this stiffening girder is here provided by the barriers. So Robert Maillart knew how to use the material and to look for synergy effects in the barrier that he needs anyway. He used this as a structural element to stiffen the arch. But the real genius of Robert Maillart comes into play when you consider how the bridge was built. He needed obviously a false work for casting the arch. And since he was entrepreneur and designer, he had to look for cost efficiency. So he wanted to design his falsework for the smallest loads possible, and that led to a slender arch. And then he used the falsework a second time and he lowered it to provide stiffness to the arch when he cast the superstructure, because you cannot cast the superstructure in a way that the arch is perfectly loaded. So this is efficiency. And on top of this, and that is a specialty of Robert Maillard, he created as well aesthetic quality that is probably for concrete bridges unmatched until today. Someone who studied Robert Maillard very, very thoroughly is Christian Menn. And he is as well from Switzerland, and he created in 1998, I would say, his masterpiece, the Suniberg Bridge in Klosters. This is an integral bridge with a length of 526 meters. You heard correctly, it's over half a kilometer long. And here you would say, what has this bridge with Robert Maillard to do? Because this is a cable stayed bridge. Some people call it an extra load bridge, but I call it more a frame structure because the columns and the superstructure are monolithically connected, and as well the superstructure is monolithically connected to the abutments. So if the bridge undergoes temperature change, it moves radially in and out, and that is the same principle that Robert Maillard used for the Valchier bridge, just that he didn't move radially or laterally, he moved vertically. These bridges breathe like your tummy is breathing when you take air in and out. And this way, they reduce the restraining effects. In order to facilitate this breathing, the piers need to be accordingly shaped so that they are flexible. But on the other hand, through the integral abutments, the superstructure provides lateral supports to the pier. So everything works together. The piers help the superstructure and the superstructure helps the piers. And that shows you the overall design philosophy. The next bridge is a bridge by Jörg Schleich in Stuttgart, in northern Stuttgart. The Heilbronner Street is bridged here by the Auerbach Street. This bridge was built in 2006 and has a length of 130 meters. What Jörg Schleich did is he combined both ideas from Robert Maillard, the deck stiffened arch that reaches vertically, with the Suniberg bridge that breathes laterally, because this bridge has an S shape and can move laterally as well. What you see here in the picture is that you have here in the back a V column, so this goes over a gas station. And I discussed this bridge with Christian Menn, who was obviously interested in what Jörg Schleich is doing. And then Christian Menn, on the way back to his hometown Chur, he sent me basically a letter. And he writes in this letter, principally, I like Schleich's bridge, especially the monolithically connection to the abutment and the elevated arch support. But I asked myself whether less would have been more. And what he means with this, reducing the arch to inclined struts, then the bridge would have been even lighter, more transparent, and more homogeneous in respect to the Y column. And you see here on his sketch what he had in mind. So when you compare his sketch with Schleich's design, you see that Schleich had here basically a load path where you have to go here to the left into this column, and then you come back. And what Menn is doing, he has a column right over this inclined column so that you have a direct load path, and he keeps these members straight. So he tries to reduce things, to simplify things, but you see he has still aesthetics in mind. So it's very interesting how these masters of bridges, how they influence each other and how they try to improve things, even when they see something that is built. So they influence each other. If you want to become a master in bridge design, you need to study bridges. You need to see what these predecessors did and understand why they did what they did. Now let's talk about design aspects of integral bridges. And I cannot talk here in length about all the various things that I present. Each of those that I here present would be a lecture on its own, but I want to give you an idea of what's possible. And if you go to the internet and you Google these things, you will find a lot of information to this. And I want to inspire you to uh, yeah, to look this up and to study these things and to understand how they affect bridge design, particularly integral bridges. The first of those important design, let's say, processes is the conceptual design, which was actually first brought up by Christian Mann. And this is an overarching early design process to develop multiple bridge options for evaluation and selection so that you can discuss this with your owner and with stakeholders and to see what suits the situation best from a constructability, from a functionality, and from a cost perspective. The next aspect is the performance-based design. I will talk more about this, but what I want to say in this context here is you need to define what this means to you. And when you ask 10 engineers, you get probably 10 different opinions of what is actually the performance-based design. And for me, it's a tailored design approach to achieve structural efficiency and best return on investment for an individual situation. The next aspect that I want to bring up is elastic design versus plastic design. So elastic design, you can just separate in linear elastic or non-linear elastic design. But I don't want to go too much into this. I want to just say, because it's, I think, not so clear to everybody, we're using elastic design for simplicity. And this is very easy to implement in models and to get more or less reasonable results. When it goes plastic, when you have non-linearity in the material, it becomes tricky because the sequence of building plastic hinges matters. And what we typically do, we don't do this on a global model because it gets too complicated. And I would not recommend complicated models. But it's important to understand what happens locally, and that's where the plastic design is coming into play, because you want to know, is that a brittle failure mode or is it a ductile failure mode? And if it's a ductile failure mode, what type of rotations or deformations can you actually endure? Another important aspect in bridge design, and probably not just in bridge design, in generally in design and lightweight design principles. I will say that later we need to achieve more with less because of climate change, of sustainability um, um, requirements, because we can't just take the material for granted and saying it's just there. So we need to go back to the roots when material was expensive and labor was cheap. Today, labor is expensive, material is cheap, and that's probably something that our structures suffer from. And we can create lightweight bridges. We save not just material, we create better structures. I'm really convinced about this because we need to think about where to put the material so that it works for us best. Solid structure interaction, I mentioned this already, is an important aspect of integral bridge design simply because the soil matters. If you have stiff soils, you have larger restraining effects. If you have soft soils, you have larger deformations, and you need to understand what matters and what you can tolerate. For that reason, I recommend the lower and upper bound solid spring approach, where you study how your bridge behaves to those soil conditions, and then you tune your bridge with the slenderness, with the stiffness of its members, so that it has the right performance that you would like to see. And another important aspect, which is a relative new approach, is the failure mechanism design philosophy, where you push your structure to the limits and you want to understand what failure mechanisms are developing, in what sequence, and in what behavior. That helps you actually to identify the weak spots in your structure, and when you properly design them, you can use them actually as fuses so that they protect elements that are more critical in terms of a brittle failure mode. So we do this already in seismic design. We call it there the capacity protective design approach. Then I would like to say something, especially to our younger engineers, FE models versus hand calculations and spreadsheets. I think hand calculations are still in today's world a very powerful tool for several reasons. First of all, you have to be uh, someone who needs to know what you're doing because with a piece of paper and a pencil, you can't do anything when you don't know what you do. Secondly, you need to aim for simplicity and transparency. So you need to look for symmetry, you need to look for all the kind of features that you can get to keep things simple. And you need to be very clear about what assumptions you are making. And this is often ignored because the assumptions that you make as an engineer, you need to verify them later when your design is there. Otherwise, you may introduce flaws and don't find acceptance. So the power of hand calculation is this: you know already what to expect when you get your structure into the computer. And you have a very good, let's say, way of validating computer results. If you don't know what the computer will produce, you are basically relying on the computer results, and this can be very, very dangerous. So I'm not saying that the program is doing the wrong thing, but you may have put the wrong values in, or you have made the wrong assumptions. And this is the power of spreadsheets and hand calculations. Do both. And there is another aspect that I would like to mention. When you can guess what the results are, you become the better engineer because you have to make engineering judgment calls ultimately. You cannot analyze everything. And you need to develop a feeling for the structure. You need to know what works and what doesn't work. And this is the best way done by hand calculations. Another aspect, we have heard this, the load path analogies. So we try to find load paths for vertical loads, for lateral loads, and we want to understand how complex details work. And this is best done via static time models because they visualize the flow of forces. They show you what's happening in a critical model, and that gives you a good sense of how to reinforce complex concrete details. I like to differentiate between primary components and secondary components, and to give you an example, my YAS Fallschild bridge that I presented to you, the primary components are the arch, the wall, but the secondary component would be the barrier, the stiffening girder. So they need each other. Without the arch, the barrier couldn't span the 55 meters. Without the barrier, the arch couldn't handle uh, unsymmetrical loads. So the secondary components are very important too, but they are secondary because they are not necessarily the primary load path for that load. I mentioned this already, simplicity when it comes to the design and when it comes to the traceability of your results. But the simplicity is very important as well for aesthetics. And please allow me to speak here about aesthetics because not many bridge engineers talk about aesthetics, and I think this is sad to see because our structures are very important. They are not just serving a function, they create a new space. So in some cities, when you think about Sydney, for example, or San Francisco, what would be those cities without their bridges? And other smaller bridges, they define sometimes as well a location. And I think the Suniberg Bridge and the Waldschil Bridge are good examples for this. So simplicity is key in order to create a good looking structure, avoid complex systems, and make sure that the dominant structural system, the primary load path, is good visible. Another aspect is the scale factor. So it's important that you have the right system for the right scale. It doesn't make sense to build a suspension bridge for a 10-meter span or a beam structure for a 350-meter span. Have the right proportions of the structural components to each other. So when you have a very thick superstructure and have very slender columns, that's probably not a good idea, and vice versa. So make sure that the proportions are well addressed, and then they probably are working well from a structural perspective as well. Care about structural details. I cannot emphasize this enough because structural details need to work. Your structure is only as good as the weakest detail. And if you do it right, it typically looks good too. If it looks wrong, something is wrong. So make sure your structural details are well designed and taken care of, because if you use that as a, yeah, it will work somehow, put some reinforcement in it, it's good. It's not a good approach. If you have in the conceptual design stage, innovative design, and you don't have the solutions for the structural details, take care right away of the structural details, because this should not be an afterthought. Another aspect that is important for aesthetics is texture, how you play with the surface in order to create light and shadows to improve as well durability, that the water is not sitting there or bringing dirt to certain critical components. Make sure this is all well addressed in your design, then you create a durable and good looking structure. And last but not least, slenderness and transparency. Those are very, very important aspects when it comes to elegance. So slenderness is not just important from an elegance perspective, it is important as well from a structural perspective, because if you can focus the material where it makes most sense, you get then good stresses in the material. For example, a slender column has high compressive stresses, and that means you don't get really cracking, but you still have the flexibility. And it can help even in steel when you have, for example, higher compressive stresses locally, because then you may not get fatigue issues. Now let's talk about the performance-based design and compare this with a design-based performance. So that sounds a little bit intriguing, this kind of comparison. But let's talk first about what means performance-based design. That means you design for a specific performance in mind. So and the reason why you do this is you want to address the needs, the likelihood of extreme events, and for economical reasons, you want to make sure that the bridge performs according to a set standard. And we do this when it comes to seismic design already. And for example, when you look at the highway bridge design code, the Canadian Highway Bridge Design Code defines for 3 specific design scenarios, earthquake scenarios, 4 different service and damage levels, which are forming the performance criteria. And the owner can select based on what bridge type and importance the bridge has, what service and damage he or she want to see in those seismic events. But what means now a design-based performance? That means you want to get actually the best performance possible. So the performance isn't set. You as a designer go beyond what the code requires. You want, for example, protect a superstructure even if a column is taken out so that there is no collapse. That may be not a design requirement, but you want to do this because it doesn't cost you much extra, because you have a structured system that can deliver this performance. And it would be a shame when you wouldn't invest a thought into doing this to build a better structure. But this requires a good understanding of stiffness and structural behavior, and then it allows you to improve structural performance. What is now structural performance? Structural performance can be described as a bridge's behavior that satisfies safety, functionality, durability, maintenance, and other aspects. And let me focus here just on the four aspects that I mentioned: safety, functionality, durability, and maintenance. When it comes to safety, we typically making sure that our demands are not exceeding the resistance of structural members. But structural performance at the ULS level is not really investigated except for seismic design. And this is actually a flaw, because if you understand how a bridge undergoes distress and what that means to the structure and what it may trigger for consequences, you design the better bridge. And one way of doing this is using the failure mechanism concept. You study basically the failure mechanism that are building in the bridge when you push it to the limits. In seismic design, we're doing this already. Think about a pushover analysis, where you push the bridge to its limits in order to see what is the displacement capacity of the structure when, for example, on a frame, kick the P delta effects in and basically the bridge goes on its own. So you want to understand the limits. You may never reach the limits in a typical ULS scenario, but you want to understand it because this understanding is so essential for designing better bridges. The next aspect is functionality, so you call it in the code serviceability. An understanding of structural behavior, again, is essential for designing integral bridges because you have a hyperstatic system and stiffness matters when estimating forces and displacement demands for critical bridge components. So you determine if the functionality of your bridge is given when you understand what deformations the bridge sees and what forces the bridge sees and what does it do to the structure in a long-term, say, setting when cracks are building, when you see that there are certain demands, maybe even exceeding what you expected. So what happens then? Is that something you can tolerate or not? And when it comes to durability and maintenance, I put these two aspects together because they are related to each other. We know that many bridges show early signs of deterioration and require already rehabilitation during its service life. And this is definitely not desired from a sustainability perspective. A design for superior performance, so the best that you can do, tries to achieve more with less. This is best done by developing structures with slender cross-section, I mentioned this before, and by avoiding bearing and expansion joints. And that leads straight into lightweight design principles when we talk about slender members and when we talk about bridges without bearings and joints, then we're talking about integral bridges. So now I want to give you three examples. Here, this is the first example, the Lafayette-Steg in Stuttgart-Suppenhausen. And what you see here is this is a very, very slender superstructure that follows the principle of the Suniberg bridge with a curved, in plan view curved superstructure that can avoid restraining effects due to temperature change by radially moving in and out. And in order to facilitate this, and you have to look carefully for this to find this, you see here very, very slender columns. So they are so slender that you almost don't see them. They are more slender than this power line post or the trees. So that's why one architect said to me, this bridge is floating because I don't see the columns. And typically what we do is we have concrete columns and we have a steel superstructure. What we have done here is we have a concrete superstructure on steel columns. So the idea behind this is to reduce the bridge length as far as possible. Here on the left side, that was the highest point. There was a school and a pool. We wanted to bring the children safely over there and keep them away from the road as best as possible. And then this geometry made the most sense. And when you have that kind of curved opportunity, then you should see right away this is a great opportunity for making an integral bridge, even if the bridge is relatively long. And you need to design now this bridge so that this movement can happen. And you see this now in the cross section here at the column number 1, right next to the road. We have only a 750 millimeter deep superstructure T-beam that's relative wide because it needs the torsional stiffness. But the torsion is just handled at the abutments, and through the curvature there is an interaction between torsional moments and longitudinal moments, but I can't discuss this here in detail. But the interesting part is the column is taking only the vertical load, nothing else, no lateral load or torsion. And in order to facilitate the movement, the lateral movement, this column has a special shape, has two bottlenecks on the top and the bottom, so that it can act as a pendulum, but there are no bearings. These steel cast members are shaped like a wheat beer glass. We call them in Germany wheat beer glasses. And they have an extreme long bottleneck in order to allow rotations that are more or less elastic during the temperature movement. Here is a developed elevation. You see the main span is 28.5 meters, and that is quite something for a superstructure depth of just 750 millimeters. And this is only possible because you have this large abutment that provides the negative moment resistance that frames in the superstructure and sucks basically the moments away from the column. And this capacity that this abutment provides allows you actually to lose this column due to vehicle impact without having the bridge coming down and being a potential hazard for trains that run into the bridge. We had a big accident with a high-speed train in Germany where a car was derailing, taking out a bridge pier, and all the other cars were hitting the rubble of the bridge, and many people died. And that was pretty scary for me. So when I saw this bridge here, I said, we can do better than this. We need to make sure when there's a train coming downhill that cannot stop, that the bridge, even when it comes, deflects significantly, that the train has an escape route, an escape corridor underneath the bridge that can save an extreme event life. And that shows you the design for a specific performance. And that's a performance-based design all about, although this bridge had nothing to do with seismic. Here you see the situation with the large abutment and with this column. It is protected with a vehicle impact protection structure. But if there comes a major truck that aims straight for the bridge, I don't believe that this device will help you to protect the column, but the bridge will stay up, and that's important. And this you couldn't do with a bridge that is on bearings. But with an integral bridge where the superstructure is framed in, it's held back, and where the negative moment capacity is provided, you can do this. And that way you create the better structures. You see here another picture. You see the staircase here, that was a request by the city. This was not part of the competition. But we put this staircase on without any structural function for the bridge. You can take that anytime away. And it's like a staircase that you roll onto an airplane, and it's just an access provider, but the bridge can stand alone. The second example that I have here is a highway underpass near Winnenden, north of Stuttgart. Here, a new highway was built, a new ramp structure, access and ramp was created, and that's obviously a great opportunity for a bridge engineer because you don't need to deal with traffic during construction. The interesting part here is you see ideas from Robert Maillard and from Christian Menn and from Jörg Schleich in this. So these three engineers, they influenced me obviously when coming up with these ideas. But this situation, every situation is different and requires a tailored solution. And you see here, the highway is curved. The ramp is somehow a little skewed to the highway axis. And then you will see later on that the highway has as well the northbound and the southbound structure, they have an elevation difference where they come close to each other. And that led to an idea to have two individual bridges, to have each bridge with two arches, and that increases again structural redundancy. In the conceptual design phase, we investigated two different concepts. So on the top, the one that was built, a structure, I call it this Y column, but you see the arch in the structure where the centerpiece of the arch melts together with the slab of the superstructure. On the second one, where the arch is a dominant feature, is not melting together with the superstructure, but it's very, very slender and it requires actually some stiffening in the border spans, and that's why I put there a secondary element in. I call it the boomerangs that build this kind of intersection with the arch, and that creates then, if you want, a two-hinged arch system. So the owner decided to go with number one. I would have loved to build number two, but that's how it happens sometimes. Now you see how this bridge actually works, because the soil didn't allow actually to transfer the horizontal thrust of the arch to the soil. So what do you do when you want to build an arch bridge but the soil isn't adequate? So then you think this over and create not an earth anchored system, you create a self anchored system. So we take the horizontal thrust that we have here and bring it up to the small abutments on the top. And then we tie it with tendons together so that the concrete sees always compression, although this is a self-anchored system. And this system behaves a little bit like an inverted cable stayed bridge, because if you put live load in the center of the span, what you will find is that the abutments want to come up because the entire system want to rotate here around the arch support locations. And that's exactly what happens on a cable stayed bridge, and that's why you have the anchor piers and the anchor cables. So I don't have anchor cables here, but I have anchor piles. Those piles will see no tension under SLS conditions, but under ULS conditions, and that's why they are important, because they help to increase the stiffness for vertical loads, but they are not increasing the stiffness for horizontal loads. So, for example, these piles are very flexible and the bridge can still nicely expand and contract, but it's still stiff for vertical loads. And this is performance-based design. You build your structure so that you get the performance you want to see in the structure. Here is in the cross section, you see what I mentioned. The roadway design had the center line of the northbound roadway profile and this southbound roadway profile at the same elevation with that significant crossfall. You get a step, and the right answer to this was basically build two individual structures. So you can take one structure out if you want, the other one is not affected by this. Then what we did is we built a model. So no one has these skills today anymore, but that's what we did. We built a model for the bridge that was built and for the bridge that I wanted to build. So we had two models. The owner could take them from every angle, can look at this and can verify that the design objective, avoiding the tunnel effect, is actually met. And this model shows you how close this gets to the reality when you look at now the built structure, and you see now the four arches. You see here how the bridges are a little bit offset against each other. This was not incorporated in the model, but you see it here in the reality. And you see as well that the deck slab is curved in order to mimic the moment demands that it sees, and that even the legs of the arch are slightly curved in order to enhance slenderness and aesthetics. So the last example that I have here is the Hunt Creek pedestrian bridge in Surrey. Yeah, when you see this, you would think this is a truss bridge, but it's more than this. I call it an integral hybrid fish belly truss suspension bridge. So you see you have several systems in this system, and you need to be very careful to make sure during the design and the construction that you activate those systems the way you want to see them. So you need to incorporate now the construction process into the design in order to get what you want. And the key design that you need to address in the conceptual design phase is this abutment, because this abutment is everything. Everything comes together here. And you see here, when you look carefully, you see strut and tie models, and you see here how these separate members are actually anchored. So you have a kind of a table. I call it sometimes a pier table, but here in this case, you would call it an abutment table. And there are 4 piles, so 2 in each row. You see only 2, but there are 2 basically behind the first ones. And these 4 build this table. And then you have the suspension system here, which is the bottom chord of the truss that is anchored here on the back side, and that meets basically here right above the centroid of the table. And you see this strut and tie model, how the vertical loads of this suspension system are transferred nicely to the parts. And then you see here the rock anchor. You can call this the backstays if you want. And they take the horizontal part out because you don't want to take the horizontal part actually with the parts. Now, from a construction perspective, you don't want to see much movement in this table. So you need to stress these solid anchors first, but when you stress them against what are you stressing? Because then you would pull that table back. So we didn't need this center soil anchor, so we put a micropile instead of this soil anchor in, and that micropile acts as a pile and resists actually these soil anchor forces. And then when we start loading these suspension cables, then we just take the load from the micropile away, and then you don't see much movement. That was the idea. Now, how is this structure built? So first you install the cables that are actually 2 truss cords. So this is, if you want, 2 bottom cords, but each bottom cord has 2 cables for redundancy reasons, and it would even allow to change one suspension cable at a time while you still have live load on the bridge, because you can lower this cable and let it come down and then pull another cable in. The other cable would keep the bridge up. And this hasn't been done by any means for suspension bridge yet. So you see how you can develop a performance of the structure that is new. Now, the reason why we developed this system was the city didn't want to cut down trees, and they wanted to keep the corridor as narrow as possible, and that provides not good access for crane or for heavy duty equipment. And what you see, this truss, this was supposed to be pre-assembled as sawhorses and flying in by a very light crane, and then this was all built, stick built together. You get a sacrificial form in form of a corrugated metal sheet on top, and then you cast a concrete slab, make this top chord monolithically with the abutments, and in that moment, when the fresh concrete hardens, you establish the truss action. But all the dead load up to this moment goes purely to the suspension system. And when the truss is established and you add now additional loads like live load, then you see that you have actually a negative moment capacity at the abutments, because you have lever arm there, and that gives you now a very stiff structure. But for temperature effects, the structure is still very soft because we had a little bit of bow in the deck, so it can breathe again. And for seismic, it's as well very, very stiff laterally and longitudinally because of the rock anchors. Now, how you deal with these diagonals in the truss, because you have this kind of fish belly system, and the fish belly systems have the problem that that when you keep the the spacing of the nodes equal, that the angles get more and more shallow as you get to the end. And that creates issues, especially at the ends. You have the large shear forces and then very shallow and long members, and you don't want to see this in long members. So the idea was, how can I keep the demands in the member so that I can use everywhere the same cross section for the diagonals. I have the long members, I want to have small shear forces, and where I have the large shear force, I want to have short members. And you can say, let's try to make them all with an equal angle, but this doesn't look so good. And what we did here is basically we use these circles that have the center point on a horizontal line, and then these circles touch each other. And you see now the top chord nodes are everywhere vertically measured over the centroid of the circle, and the bottom chord nodes are always where the circles are touching each other. And now you get a very steady reduction of the node spaces, and that helps you to create this kind of aesthetic that basically is determined by how the bottom chord comes up to this horizontal line. So now I would like to speak a little bit about the future of integral bridges. As I demonstrated, the bridge lengths can be very long and exceed by far the limitations that you find here in North America in the codes. And just think about the Roman viaducts and aqueducts. They were already very long, and they had no bearings and expansion joints, and they're still around there and they work perfectly. The bridge geometry, all types of bridges can be designed with monolithic connections to abutments and piers if you take the restraining effects and the deformations into account and design accordingly. From a structural systems perspective, you deal now with hyperstatic structural systems, and they are obviously a little bit more complicated because stiffness matters when compared to structurally determined systems. So, and you shouldn't see that as a disadvantage, you should see that as an advantage, because hyperstructural systems, hyperstatic structural systems, they can activate secondary load passes because you have that structural redundancy. But you need to aim for it, and you need to design for that performance. And that's where the performance-based design comes into play. In terms of bridge types, you can basically use any bridge type. You can have a girder bridge, you can have a frame structure. The girder bridge you saw on the Lafayette Weg. The frame structures you saw in Christian Mann-Suniberg bridges. You can have arches, you saw that on Maillard and Schleik's bridges. You can have cable-supported bridges, you think about Mann's structure. And you can have even a combination of different types, as long as you maintain the simplicity and dominant load pass principles. From a materials perspective, you can use any material, concrete, steel, timber, or a combination of those compositely or non-compositely, and that includes even advanced materials like ultra-high performance concrete. From a seismic perspective, I believe that integral bridges have a superior behavior because they allow you to activate passive soil pressure behind the abutments, which you get basically for free. And you can tune those bridges with the slenderness of its members so that they achieve the best seismic performance, and you don't need necessarily isolators. Now I want to show you an example of a futuristic integral bridge. This was a conceptual design for the Nizitlin Bay Bridge in the Yukon, a curved structure, extradose structure that was supposed to be launched along the curve. And when you have flexible piers, you don't need any bearings. If ice pressure is an issue and you need to build the pier so that they can resist the ice pressure, then you would utilize bearings that allow deformations in the radial direction. Now I come to my conclusions and a summary. Integral bridges can be more than just the girder type bridge. Hyperstatic structural systems are typical and desired for integral bridges, as I explained this. Soil structure interaction is important and needs to be considered. I would do this with a lower and upper bound springs for the soils. Built-in structural redundancy increases reliability and safety. Construction and maintenance costs can be lowered when joints and bearings are avoided. Elimination of joints and bearings improves user comfort and avoids durability issues. Think about leaking joints. Lightweight design principles are possible and recommended. Continuity, slenderness, and transparency can meaningfully improve aesthetics, and you can get an improved performance when using the performance-based design approach. And now I hope that I inspired you to create better bridges by using the performance-based design and by creating integral bridge structures. Thank you.
Thank you so much, Matthias. We do have some questions if you don't mind.
Sure.
We have 2 minutes. So the first question asks, how critical is temperature for an integral bridge? Can it be cable stay or spandrel arch, which you showed us?
Yeah, you need to consider the temperature effects. You need to understand what it does to your structure, but the more flexible your structure is, the easier you can avoid these restraining effects, and that will help you to deal with this. So you just need to investigate this, and curved structures can easily move out. When you have a straight structure, you need to cope with this somehow at the abutments. We do this typically with the piles, but I believe when you have curvature in your superstructure, in plan view or vertically, you don't need the piles that need to move.
Okay, the next question asks, what is the maximum single span integral bridge that has been built or can be designed?
Good question. I think the maximum span for an integral bridge, so span depends on the moments for vertical loads, because the larger the span gets, obviously, the more heavy duty gets the superstructure. But when you think about cable supported bridges, suspension bridges, or so on, Jörg Schleich showed this through various pedestrian bridges that you can actually build very long spans with cable supported structures as long as you take care of the restraining effects. And then he does this way that actually the monolithically um, connected superstructure to the abutments is stabilizing somehow else the superstructure, so that you, for example, may need only one cable plane to support the superstructure when you have the torsional stiffness. So there is a bridge which is not a very big bridge in the German Museum in Munich, designed by Jörg Schleich, which is a fun bridge to experience. And it is, if you want, an integral bridge, but you could build that bridge in a very, very large scale if you want. And that shows you there is actually no limitations. You need just to understand structural behavior.
Okay, the next question asks, to make a long span bridge integral, is it necessary to make it curved, as in to allow radial or lateral deformation? And if not,
Not
how can we
necessarily.
accommodate,
Yeah,
sorry.
please. Sorry for interrupting.
Um, the second part is, if not, how can we accommodate the deformation?
So when you have a long span bridge and a major structure, say cable supported, you can do this with the piers. And I think Christian Menn showed that with the Sunnyback bridge. So when you want to control the movements, you can do this with the piers when they're slender enough. The problem occurs what happens at the abutments, because at the abutments you have to transition to the soil. So you can have abutments moving as well, but then where are you taking out those movements that are coming? So if the abutment shall not move, then you need to have the bridge moving vertically or laterally. But you can build as well so a transition span to the abutments so that you redistribute the deformations continually into the soil. That requires then some special techniques in terms of pavement and so on. They have done this in Austria for a bridge, but this isn't well developed yet, this field. But you can do this for longer bridges as well, but it requires an interdisciplinary reviews from a geotechnical, from a pavement engineer. So I'm not so familiar with reinforced pavement, but this is maybe a way of redistributing those kind of deformations.
Okay. Our next question says, how does the fill behind the abutment contribute to the modeling? Sorry, contribute
That's a
in the
very
modeling.
good question. That depends on how you compact the fill behind the abutment and when it's compacted and how does it behave. But typically you consider this with a spring. The problem is with a passive soil pressure that it's a nonlinear spring. So the more you push, the more is the resistance. So it's not a linear one. And typically what you do is you have a PY curve, so you have the force and you have the deformation of the soil accordingly. And then you need to iterate in your model to see that the deformation and the force that you get from your model that matches so that you have the right performance.
Okay, and then our next and final question says, can we use pre-stressed concrete beams for curved section as well? Usually in Texas, concrete girders are straight and steel are preferred for curve.
So there are two aspects when we talk about pre-stressed concrete, and I'm happy to see that question. The first aspect is when you have a curved pre-stressed girder, people think that the tenants want to pull somewhere out of the cross section, but there is a counteracting force because it's a self-anchored system. You anchor the tenants against the concrete, so the tenant want to move inwards, and the concrete that has the compression want to move out, and that's the forces that you have to balance. So having a post tension or a girder in a curved configuration is absolutely possible and it's not creating headaches. The problem is pre-stressed concrete, it doesn't crack. It's not supposed to crack under service load because you want to protect your tenants. And when your concrete doesn't crack, it's much stiffer. And that stiffness hurts you when it comes to integral bridges because you actually like the bridge to crack. So that bridge that I showed in Winneden, where we needed the tenons in order to counterbalance these self-anchored forces, they make the bridge very stiff. So you have to cope now with all the deformations at the abutments, and that's why we have these approach slabs there. So you need to be aware of when you have a post-tension or a pre-stressed system, the bridge is stiffer and cannot accommodate with cracking basically some of the temperature movements. And as I said, stiffness is something that can hurt you in an integral bridge. Yes.
Okay, we do have some more questions, but we're running a little bit out of time. So I will email those after this session. If anybody else has any more questions, feel free to submit them to hello at midasoft.com. Matthias, thank you so much for our session today. I know everybody really enjoyed it, and they were very interested in your discussion today. So thank you.
You're welcome. It was a pleasure to be here. Thank you.
Have a great day, everybody.
Thank you. Bye.